This episode is brought to you by Cisco Educational Premium. Do you know that the equations of motion describe the behavior of a physical system? In physics, equation of motion describe the behavior of a physical system in terms of its motion as a function of time. The functions are defined in a Euclidean space in classical mechanics, but are replaced by curved spaces in relativity. Did you know that the first equation of motion is v is equal to u plus at? How do we derive this equation? When we rearrange the equation for acceleration a is equal to v minus u on t, and then we make v the subject of the formula, we get v is equal to u plus at, our equation of motion. Did you know that we can derive the first equation of motion using calculus? We know that the acceleration, the formula for acceleration is a dv dt. So rearranging this, we get a dt is equal to dv. Then after integrating both sides, we get integral from 0 to t a dt is equivalent to integral from mu to v dv, which equals at is equal to u is equal to v minus u. Then rearranging, we get our first equation of motion, v is equal to u plus at. Did you know that we can derive the first equation of motion by graphical method? Say we have the velocity time graph for a moving object with initial velocity u and final velocity v, and the acceleration a as shown. From our graph, the velocity of a body changes from a to b in time t at a uniform rate. You can also see that bc is the final velocity and OC is the total time t. A perpendicular is drawn from B to OC. A parallel line is drawn from A to D, and another perpendicular is drawn from B to OE, as shown by the dotted lines. Those dotted lines. We can see that initial velocity U is equivalent to OA, and the final velocity V is equivalent to BC. Also, BC is equivalent to BD plus OC. Therefore, V is equal to BD plus DC, and also V is equal to BD plus OA, since of course DC is equivalent to OA. And so we have V to be equivalent to BD plus U, since OA is equivalent to U. Let us call this our equation 1. Since the slope of the velocity time graph is equal to the acceleration a, we have a to be equivalent to the slope of line AB, which is equivalent to BD on AD. And so since AD is equivalent to AC is equivalent to T, the above equation becomes BD, which is equivalent to AT. Let us call this our equation 2, shall we? Now, finally combining those two equations, we get V is equivalent to U plus AT, which is our first equation of motion. Did you know the second equation of motion is S is equal to UT plus half AT square? How do we derive this? From the first equation of motion, V is equal to U plus AT. We know that S is U plus V on 2 times T for linear systems where velocity is not constant. Then substituting the value of V from the first equation of motion, we get S is equivalent to U to bracket U plus AT bracket, then close the bigger bracket on 2 times T, which is equivalent to 2U plus AT times T on 2, which is also equivalent to 2U on 2 plus AT on 2 times T, which is equivalent to bracket U plus half AT bracket times T, Making further simplification and cleaning this, we get the equation S is equivalent to ut plus half at square. Did you know that we can derive the second equation of motion using calculus method? Mathematically, we can have velocity v to be ds on dt, and rearranging this we get ds is equivalent to v dt. Then substituting the first equation of motion to this, we get ds is equivalent to bracket u plus at bracket dt, which is equivalent to bracket u plus at dt, which is equivalent to bracket u dt plus at dt bracket. Integrating both sides, we get integral from 0 to s ds is equivalent to integral from 0 to 2 u dt plus integral from 0 to t at dt is equivalent to s is equal to ut plus half at square. Our second equation of motion. Did you know that we can derive the second equation using graphical method? Say we have the velocity time graph as shown there. Using our graph, we can do some deductions. Distance traveled S is equivalent to the area of the figure OABC, which is equivalent to the area of rectangle OADC plus the area of the triangle ABD. And so S is equivalent to half times AD times BD plus OA plus bracket OA plus OC bracket. Since OA is equivalent to U and OC is equivalent to T, we get this equation as S is equivalent to bracket half times AD times BD bracket plus bracket U times T bracket. We know that the BD is equivalent to AT, so the equation becomes S is equivalent to half times T times AT plus UT. And doing some simplification and cleanup, we get our second equation of motion S is equivalent to UT plus half AT square. Did you know that that equation of motion is V square plus U square plus 2AS? We can derive this equation by algebraic method. Mathematically, we know that displacement is equivalent to initial velocity plus final velocity on 2. So we have S is equivalent to U plus V on 2 times T. From the first equation of motion, we have V is equivalent to U plus AT. So rearranging the above formula, we get T is equivalent to V minus U on A. Now, substituting T in the displacement formula, we get S is equivalent to V plus U on 2, V plus U on A, is equivalent to V square minus U square on 2A. So then we get 2AS is equivalent to V square minus U square. And rearranging, doing some cleanup, we get V square is equivalent to U square plus 2AS. Did you know that the third equation of motion can be derived from calculus? We know that acceleration is the rate of change in velocity and can be written as A is equivalent to dv dt. Let us call this our equation 1. We also know that velocity is the rate of change of displacement and can be expressed as V is equivalent to ds on dt. Let us call this our equation 2. So it follows that we cross multiply our two equations. We get A ds on dt is equivalent to V dv on dt. And so integrating from 0 to s A ds, it will be equivalent to integral from u to v dv. We will obtain the result as v square minus u on 2. Then doing some rearrangement, we get v square is equivalent to u square plus 2as. Our third equation of motion, by the way. At times you are getting an answer and you already forgotten the question. Did you know that we can derive the third equation of motion by a graphical method? Take a look at the velocity time graph. Our graph has all the information we require. And so we know that the total distance traveled S is given by the area of the trapezium OABZ. Therefore, S is equivalent to half sum of parallel sides times height, which is equivalent to half times bracket OA plus CB bracket times OC. Since we know that OA is equivalent to U, CB is equivalent to V, and OC is equivalent to T, the equation thus become S is equivalent to half times bracket U plus V times T, and since T is equivalent to bracket V minus U on A, the above equation can be written as S is equivalent to half times bracket V plus U bracket times bracket V minus U on A, which is equivalent to V square minus U square on 2A. Then engaging the brain just a little bit and solving this, we get our third equation of motion. V square is equivalent to U square plus 2AS. This episode is brought to you by Cisco Educational Premium. Did you know that Lippmann-Schwinger equation is consistent with Schrödinger equation? The Lippmann-Schwinger equation is one of the most used equations to describe particle collisions, or more precisely scattering in quantum mechanics. It may be used in scattering of molecules, atoms, neutrons, photons, or any other particles, and is important mainly in atomic, molecular, and optical physics, nuclear physics, and particle physics, but also for seismic scattering problems in geophysics. It relates the scattering wave function with the interaction that produces the scattering potential, and therefore allows calculation of the relevant experimental parameters, scattering amplitude and cross sections. The most fundamental equation to describe any quantum phenomenon, including scattering, is the Schrödinger equation. In physical problems, this differential equation must be solved with the input of an additional set of initial or boundary conditions for the specific physical system studied. The Lippmann-Schwinger equation is equivalent to the Schrödinger equation plus the typical boundary conditions for scattering problems. In order to embed the boundary conditions, the Lippmann-Schwinger equation must be written as an integral equation. For scattering problems, the Lippmann-Schwinger equation is often more convenient than the original Schrödinger equation. The Lippmann-Schwinger equation is useful in a very lineup of situations involving two-body scattering. For three or more colliding bodies, it does not work well because of the mathematical limitations. For diff equations may be used instead. However, there are approximations that can reduce a many-body problem to a two-body problems to a set of two-body problems in a variety of cases. For example, in a collision between electrons and molecules, there may be tens or hundreds of particles involved, but the phenomenon may be reduced to a two-body problem by describing all the molecule constituent particle potential together with the pseudo-potential. In these cases, the Lippmann-Schwinger equations may be used. Of course, the main motivation of these approaches are also the possibility of doing the calculation with much lower computational efforts. From the mathematical point of view, the Lippmann-Schwinger equation in coordinate representation is an integral equation of Fredholm type. It can be solved by discretization. Since this is equivalent to the differential time-independent Schrödinger equation with appropriate boundary conditions, it can also be solved by numerical methods for differential equations. In the case of the spherically symmetric potential V, It is usually solved by partial wave analysis. For high energies or weak potential, it can be solved perturbatively by means of bond series. The method convenient also in the case of many body physics, like in description of atomic, nuclear, or molecular collisions, is the method of the R matrix Wigner and Eisenberg. Another class of methods is based on separable, separable, separable expansion of the potential of green operator, like the method of continued fractions of Harak and Sasakawa. Very important class of methods is based on variational principles. For example, the Schwinger-Langossos method combining the variational principle of Schwinger with Langossos algorithm. In the S matrix formulation of particle physics, which was pioneered by John Agbiwald Wheeler, among others, all physical processes are modeled according to the following paradigm. One begins with a non-interacting multiparticle state in the distant past. Non-interacting does not mean that all of the forces have been turned off, in which case, for example, protons will fall apart, but rather that there exists an interaction-free Hamiltonian H0 for which the bound states have the same energy level spectrum as the actual Hamiltonian. This initial state is referred to as the in state. Intuitively, it consists of elementary particles or bound states that are sufficiently well separated that their interaction with each other are ignored. The idea is that whatever physical process one is trying to study may be modeled as scattering process of these well separated bound states. This process is described by the full Hamiltonian, but once it's over, all of the new elementary particles and new bound states separate again, and one finds a new non-interacting state called the out state. The S matrix is more symmetric under relativity than the Hamiltonian because it does not require a choice of time slices to define. This paradigm allows one to calculate the probabilities of all the processes that we have observed in 70 years of particle collider experiments with remarkable accuracy. But many interesting physical phenomena do not obviously fit into this paradigm. For example, if one wishes to consider the dynamics inside of a neutron star, sometimes one wants to know more than what it will finally decay into. In other words, one may be interested in measurements that are not in the asymptotic future. Sometimes an asymptotic past or future is not even available. For example, it is very possible that there is no past before the Big Bang. In 1960s, the S-matrix paradigm was elevated by many physicists to a fundamental law of nature. In S-matrix theory, it was stated that any quantity that one could measure should be found in the S-matrix for some process. This idea was inspired by the physical interpretation that S-matrix techniques could give to Feynman diagram restricted to the mass shell and led to the construction of dual resonant models. But it was very controversial because it denied the validity of quantum field theory based on local fields and Hamiltonians. Intuitively, the slightly deformed eigenfunctions of the full Hamiltonian and in and out states, the phi, are non-interacting states that resemble the in and out states in the infinite past and infinite future. This intuitive picture is not quite right because psi is an eigenfunction of the Hamiltonian. Psi raised to plus or minus is an eigenfunction of the Hamiltonian, and so at different times only differs by a phase. Thus, in particular, the physical state does not evolve, and so it cannot become non-interacting. This problem is easily circumvented by assembling psi raised to plus or minus and phi into wave packets with some distribution Ge of energies E over characteristic scale delta E. The uncertainty principle now allows the interactions of the asymptotic states to occur over a time scale reduced Planck constant on delta E. And in particular, it is no longer inconceivable that the interactions may turn off outside this interval. The following argument suggests that this is indeed the case. Plug the Lippmann-Schwinger equation into the definitions. Psi g raised to plus or minus t is equivalent to integral of dE ei e negative I et ge psi raised to plus or minus and psi gt is equivalent to integral dE e raised to negative I et g e phi of the wave packets. We see that at a given time, the difference between psi gt and phi gt wave packets is given by an integral over the energy E. This integral may be evaluated by defining the wave function over the complex E plane and closing the E contour using a semicircle on which the wave functions vanish. The integral over the closed contour may be evaluated using the Cauchy integral theorem, a search of the residues at various poles. We will now argue that the residues of psi raised to plus or minus approach those of phi at time t approaching positive or negative infinity, and so the corresponding wave packets are equal at temporal infinity. In fact, for very positive terms t and e raised to negative iet factor in a Schrödinger picture state forces one to close the contour on the lower half plane. The pole in the phi psi from the Lippmann-Schwinger equation reflects the time uncertainty of the interaction, while that in the wave packets weight functions reflect the duration of the interaction. Both of these varieties of poles occur at finite imaginary energies and so are suppressed at very large terms. The pole in the energy difference in the denominator is on the upper half plane in the case of psi, and so does not lie inside the integral contour and does not contribute to the psi integral. The remainder is equal to the phi wave packet. Thus, at very late terms, psi will be equivalent to phi, and identifying psi as the asymptotic non-interacting out state. Similarly, one may integrate the wave packet corresponding with the psi, this one raised to a positive this term, at very negative terms. In this case, the contour needs to be closed over the upper half plane, which therefore misses the energy pole of psi, which is the lower half plane. One then finds that the psi and the phi wave packets are equal in asymptotic past, identifying psi as the asymptotic non-interacting in state. This identification of the psi's as asymptotic states is the justification of the plus or minus epsilon in the denominator of the Lippmann-Schwinger equations. The S matrix is defined to be the inner product. SAB is equivalent to psi raised to negative A plus psi raised to positive B of the earth and bith Eisenberg picture asymptotic states. One may obtain a formula relating the S matrix to the potential V using the above contour integral strategy, but this time switching the roles of positive psi and negative psi. As a result, the contour now pick up the energy pole. This can be related to the phi's if one uses the S matrix to swap the two sides. Identifying the coefficients of the size on both sides of the equation, one finds the desired formula relating to the S potential. In the Born approximation, the corresponding to the first order perturbation theory, one replaces this last psi with the corresponding eigenfunction phi of the free Hamiltonian, yielding SAB is equivalent to sigma A minus B minus 2I pi sigma EA minus EB phi A V phi B, which expresses the S matrix entirely in terms of V and free Hamiltonian eigenfunctions. These formulas may in turn be used to calculate the reaction rate of the process B as it approaches A, which is equal to SAB minus sigma AB squared. With the use of the Green's function, the Lippmann-Schwinger equation has counterparts in homogenization theory, like mechanics, conductivity, and permittivity. This episode is brought to you by Cisco Educational Premium. Did you know that Schrödinger equation is a partial differential equation? Schrödinger equation tells us everything we need to know about a quantum system. The Newton's equation F is equal to ma tells us everything we need to know about the macro world around us, while the Schrödinger equation tells us everything we need to know about the quantum micro world below. Schrödinger equation governs the wave function of a quantum mechanical system. It gives the evolution of a wave function which describes an isolated quantum mechanical system. Schrödinger equation was postulated in 1925. It was postulated by Erwin Schrödinger. Erwin used William Rowan's Hamilton analogy between mechanics and optics to formulate it, but it was only good for describing quantum mechanical system. He wasn't sure with its meaning. Quite pragmatic, such a stereotype scientist. He published it in 1926 and was awarded the 1933 Nobel Prize in Physics. Schrödinger equation is analogous to the classical energy equation. Energy equation we are talking about here is energy is equivalent to kinetic energy plus potential energy. Schrödinger equation is I reduce Planck's constant H partial on partial T, the pitchfork which is called psi bracket x comma t bracket is equivalent to square brackets negative reduce Planck's constant square on 2m partial square on partial x square plus capital V bracket x comma t bracket closing the square brackets psi bracket x comma t bracket. So we have this first part representing energy, referring to the classical energy equation. Second part representing kinetic energy, and the third section representing potential energy. In Schrödinger equation, psi bracket x comma t bracket is a wave function. This is what we call a complex wave function. M is the mass of our quantum particle. Vxt, on the other hand, is the potential that represents the environment in which the particle exists. Constant I is the imaginary unit, and h is the reduced Planck's constant. Schrodinger's equation is a linear differential equation. This means that if two state vectors psi1 and psi2 are solutions, so are the linear combination psi is equivalent to a psi1 plus b psi2 of the two, where a and b are complex numbers. It's worth noting that this mathematical possibility allows for physical property of superposition of quantum states. Schrodinger equation can be applied to hydrogen atom. Schrodinger equation will evolve to E psi is equal to negative h, which is reduced Planck's constant square, on 2 mu delta square psi minus q square on 4 pi epsilon naught r psi, where q is the electron charge, r is the position of the electron relative to the nucleus, r is equivalent to magnitude of r, or vector r is the magnitude of the relative position. Potential term is due to the Coulomb interaction. Epsilon naught is the permittivity of free space, and mu is equivalent to mq mp on mq plus mp is the two-body reduced mass of the hydrogen nucleus of mass mp and electron mass. This episode is brought to you by Cisco Educational Premium. Did you know that the direct equation is consistent with Schrodinger equation? In particle physics, the Dirac equation is a relativistic wave equation derived by the British physicist Paul Dirac in 1928. In its free form, or including electromagnetic interactions, it describes all the spin-half massive particles called the Dirac particles, such as electrons and quarks, for which parity is asymmetry. It is consistent with both the principles of quantum mechanics and the theory of special relativity, and was the first theory to account fully for special relativity in the context of quantum mechanics. It was validated by accounting for the fine structure of the hydrogen spectrum in a completely rigorous way. The equation also implied the existence of a new form of matter, antimatter, previously unsuspected and unobserved, and which was experimentally confirmed several years later. It also provided a theoretical justification for the introduction of several component wave functions in Pauli's phenomenological theory of spin. The wave functions in the Dirac theory are factors of four complex numbers, known as bispinors, two of which resemble the Pauli's wave function in the non-relativistic limit, in contrast to the Schrodinger equation, in which described the wave function of only one complex value. Moreover, in the limit of zero mass, the Dirac equation reduces the Wheel equation. Although Dirac did not at first fully appreciate the importance of these results, the entire explanation of spin as a consequence of the union of quantum mechanics and relativity, and the eventual discovery of the positron, represents one of the great triumphs of theoretical physics. This accomplishment has been described as fully on par with works of Newton, Maxwell, and Einstein before him. In the context of quantum field theory, the Dirac equation is reinterpreted to describe quantum fields corresponding to the spin-half particles. In its modern formulation of the field theory, The direct equation is written in terms of a direct spin-off field psi. Take the values in a complex vector space described concretely as C4 defined on a flat spacetime Minkowski space R13. Its expression also contains gamma matrices and a parameter m greater than 0, interpreted as the mass as well as other physical constants. In terms of the field psi R13 C4, the direct equation evolved, and in natural units with Feynman slash notation, the gamma matrices are a set of 4x4 complex matrices which satisfy the defining anti-commutation relations. These matrices can be realized explicitly under choice of representation. Two common choices are the direct representation, where sigma I are the Pauli matrices, and the chiral representation, the epsilon I are the same, but epsilon 0 is equivalent to the matrix 0, I2, I2, 0. The slash notation is a compact notation for A, the slash epsilon mu, A mu, where A is a 4-factor, often it is a 4-factor differential operator, partial mu. The summation over the index mu is implied. The direct adjoint of the spin-off field psi x is defined using the property of the gamma matrices, which follows straightforwardly from hemiscity properties of the epsilon mu. One can derive the adjoint direct equation by taking the Hamilton conjugate of the direct equation and multiplying on the right by epsilon 0, where the partial derivative acts from the right on psi by x, written in the usual way in terms of the left action derivative, applying the I partial the slash plus m to direct equation. That is, each component of the direct spin-off field satisfy the Gordon equation. A conserved current of the theory is J mu is equivalent to psi bar epsilon mu psi, proving the conservation from direct equation. So we add the direct and the adjoint direct equation, and by the Leibniz rule, we have I partial mu psi bar epsilon mu psi is equivalent to 0. Another approach to derive this expression is by variational methods, applying Noether's theorem for the global U1 symmetry to the derived conserved current J mu, proving from conservation from Noether's theorem. Recall the Lagrangian. Under the U1 symmetry, which send psi and psi by, we find Lagrangian is invariant. Now, considering the variation parameter alpha to be infinitesimal, we work at the first order in alpha and ignore those terms. From the previous discussion, we immediately see the explicit variation in the Lagrangian due to alpha is vanishing. That is under the variation where the term sigma L is equivalent to 0. As part of the Noether's theorem, we find the implicit variation in the Lagrangian due to variation of fields. If the equation of motion for psi bar satisfied, then we have as follows. This immediately simplifies as there are no partial derivatives of psi bar in the Lagrangian. Sigma psi is an infinitesimal variation. Sigma psi x equivalent to I alpha psi x, and we evaluate as follows, and the equation becomes 0 is equivalent to negative alpha partial mu psi bar epsilon mu psi. We're done. Since the direct operator acts as a 4 tuples of the square integrable functions, its solution should be members of the same Hilbert space. The fact that the energies of the solution do not have a lower bound is unexpected. Plane wave solutions are those arising from the ansatz, which models a particle with a definite form momentum P is equivalent to EPP. For these ansatz, the Dirac equation becomes the equation for UP. After picking a representation for the gamma matrices epsilon mu, solving this is a matter of solving a system of linear equations. Is a representation for the property of gamma matrices. The solution space is a two-dimensional. For example, in the chiral representation for epsilon mu, the solution space is parameterized by C2 factor psi, where sigma mu is equivalent to I2 sigma I, comma, sigma bar mu is equivalent to I2, comma, minus sigma I. And the root dot is the Hamilton matrix square root. These plane wave solutions provide a starting point for canonical quantization. Both the Dirac equation and the adjoint Dirac equation can be obtained from varying the action with the specific Lagrangian density. If one varies this with respect to psi, one gets the adjoint Dirac equation. Meanwhile, if one varies this with respect to psi bar, one gets the Dirac equation. In natural units with the slash notation, for this action, the conserved current J mu above rises as the conserved current corresponds with the global U1 symmetry through Newton's theorem for field theory. Gauging this field theory by changing the symmetry to a local spacetime point dependent one gives gauge symmetry, gauge redundancy. The resultant theory is the quantum electrodynamics QED. The Dirac equation is invariant under Lorentz transformations, that is, under the action of the Lorentz group SO13 or strictly SO13 plus, the component connected to the identity. For a Dirac spinor viewed concretely as taking values in C4, the transformation under Lorentz transformation lambda is given by a 4x4 complex matrix S lambda. There are some subtleties in defining the corresponding S lambda as well as a standard abuse of notation. Most treatments occur at the Lie algebra level. The Lorentz group of 4x4 real matrices acting on R13 is generated by a set of 6 matrices M, mu, nu. When both the rho sigma indices are raised or lowered, these are simply the standard basis of antisymmetric matrices. This satisfies the Lorentz algebra commutation relations. It is also found that the spin generators satisfy the Lorentz algebra commutation relations. A Lorentz transformation lambda can be written on where the components omega mu nu are antisymmetric in mu nu. The corresponding transformation on spin space. This is an abuse of notation, but a standard one. The reason is S lambda is not a well-defined function of lambda, since there are two different sets of components, omega, mu nu, up to equivalence, which give the same lambda but different S lambda. In practice, we implicitly pick one of these omega mu nu and then S lambda in a is well defined in terms of omega mu nu. Under Lorentz transformation, the Dirac equation becomes and evolves. I think it's clear. Let us remind ourselves of the proof of Lorentz invariance. Multiplying both sides from the left by S negative 1 lambda and returning the Dama variables to x. We'll have shown invariance if it is s lambda negative 1 epsilon mu s lambda negative 1 mu is equivalent to epsilon nu. This is most easily shown at the algebra level. Supposing the transformation are parameterized by infinitesimal components omega mu nu, then at first order in omega on the left hand side, while on the right hand side, it's a standard exercise to evaluate the commutator on the left hand side. Writing the m rho sigma in terms of components completes the proof. Associated to the Lorentz variance is a conserved nether current, or rather a tensor of conserved nether currents J rho sigma nu. Similarly, since the equation is invariant under translations, there is a tensor of conserved nether currents P mu nu, which can be identified as a stress energy tensor of the theory. The Lorentz current J rho sigma nu can be written in terms of stress energy tensor, in addition to a tensor representing internal angular momentum. This episode is brought to you by Cisco Educational Premium. Did you know that spin is an inherent property of a quantum particle? Spin is a conserved quantity carried by elementary particles and thus by composite particles or hadrons and atomic nuclei. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum of orbital revolution and appears when there is a periodic structure to its wave function as the angle varies. For photons, spin is the quantum mechanical counterpart of the polarization of light. For electrons, the spin has no classical counterpart. The existence of electron spin angular momentum is inferred from experiments such as the Stern-Galach experiment, in which silver atoms were observed to possess two possible discrete angular momenta despite having no orbital angular momentum. The existence of the electron spin can be inferred theoretically from the spin statistics theorem and from the Pauli exclusion principle, and vice versa. Given the particular spin of the electron, one may derive the Pauli exclusion principle. Spin is described mathematically as a vector for some particles such as photons, and as spinors and pi spinors for other particles such as electrons. Spinors and bispinors behave similarly to vectors. They have definite magnitudes and change under rotations. However, they use an unconventional direction, and I quote, "All elementary particles of a given kind have the same magnitude of spin angular momentum, though its direction may change. These are indicated by assigning the particle a spin quantum number. The SI unit of spin is the same as classical angular momentum. In practice, spin is given as a dimensionless spin quantum number by dividing the spin angular momentum by the reduced Planck's constant, which has the same dimensions as angular momentum, although this is not the full computation of this value. Very often, the quantum number is simply called spin. The fact that it is a quantum number is implicit. As the name suggests, spin was originally conceived as the rotation of a particle around some axis. While the question of whether the elementary particles actually rotate is ambiguous, as they appear point-like. This picture is correct insofar as spin obeys the same mathematical laws as quantized angular momenta do. In particular, spin implies that the particle phase changes with angle. On the other hand, spin has some peculiar properties that distinguish it from orbital-angular momenta. These properties are: 1. Spin quantum numbers may take half-integer values. 2. Although the direction of its spin can be changed, an elementary particle cannot be made to spin faster or slower. 3. The spin of a charged particle is associated with a magnetic dipole moment with a g factor different from 1. This could occur classically only if the internal charge of the particle were distributed differently from its mass. The conventional definition of spin quantum number is S is equivalent to n on 2, where n can be any non-negative integer. Hence, the allowed values of S are 0, half 1, 3 on 2, 2, etc. The value of S for an elementary particle depends only on type of particle and cannot be altered in any known way, in contrast to the spin direction. We will be seeing the spin angular momentum S of any physical system is quantized. The allowed values of S are S equivalent to reduced Planck's constant root S on n plus 1 is equivalent to Planck's constant on 2 pi, root of n on 2, n plus 2 on 2 is equivalent to h on 4 pi, root of n into n plus 2, where h is the Planck constant and h dash is the reduced Planck's constant, which is equivalent to h on 2 pi. In contrast, orbital angular momentum can only take on integer values of S, that is even numbered values of n. Those particles which have integer spins, such as half, 3 on 2, 5 on 2, are known as fermions, while those particles with integer spins, such as 0, 1, 2, etc., are known as bosons. The two families of particles obey different rules and broadly have different roles in the world around us. A key distinction between the two families is that the fermions obey the Pauli exclusion principle. That is, they cannot be two identical fermions simultaneously having the same quantum numbers, meaning roughly having the same position, velocity, and spin direction. Fermions obey the rules of Fermi-Dirac statistics. In contrast, bosons obey the rules of Bose-Einstein statistics and have no such restriction, so they may bunch up together in identical states. Also, composite particles can have spins different from their component particles. For example, a helium photon in the ground state has spin 0 and behaves like a boson, even though the quarks and electrons which make it up are all fermions. This has some fun consequences. Number 1 is that quarks and leptons, including electrons and neutrinos, which make up what is classically known as matter, are all fermions with spin half. The common idea that matter takes up space actually comes from the Pauli exclusion principle acting on these particles to prevent the fermions from being in the same quantum state. Further compaction would require electrons to occupy the same energy states, and therefore a kind of pressure, sometimes known as degeneracy pressure of electrons, acts to resist the fermions being overly close. Elementary fermions with other spins 3 on 2, 5 on 2, etc. are not known to exist. 2. Elementary particles which are thought of as carrying forces are all bosons with spin 1. They include the photon, which carries the electromagnetic force, the gluon, which also the strong force, and the W and Z bosons, weak force. The ability of bosons to occupy the same quantum state is used in the laser, which aligns many photons having the same quantum number, the same direction and frequency. Superfluid liquid helium resulting from helium photons obeying bosons and superconductivity, where pairs of electrons, which individually are fermions, act as single composite bosons. Elementary bosons with other spins 0, 2, 3, and etc. were not historically known to exist, although they have received considerable theoretical treatment and are well established within their respective mainstream theories. In particular, theoreticians have proposed the graviton predicted to exist by some quantum gravity theories, with spin 2, and the Higgs boson explaining electroweak symmetry breaking with spin 0. Since 2013, the Higgs boson with spin 0 has been considered proven to exist. It is the first scalar elementary particle, spin 0, known to exist in nature. And the last is that atomic nuclei have a nuclear spin, which may be either half integer or integer, so that the nuclei may be either fermions or bosons. The spin statistics theorem splits particles into two groups, bosons and fermions, where bosons obey Bose-Einstein statistics and fermions obey Fermi-Dirac statistics, and therefore the Pauli exclusion principle. Specifically, the theory states that the particles with an integer spin are bosons, while all other particles have integer spins and are fermions. As an example, electrons have integer spin and are fermions that obey the Pauli exclusion principle, while photons have integer spin and do not. The theorem relies on both quantum mechanics and the theory of special relativity. This connection between spin and statistics has been called, and I quote, one of the most important applications of the special relativity theory. Since elementary particles are point-like, self-rotation is not well defined for them. However, spin implies that the phase of the particle depends on the angle as is theta for rotation of angle theta around the axis parallel to the spin s. This is equivalent to the quantum mechanical interpretation of momentum as phase dependence in the position, and of orbital angular momentum as phase dependence in the angular position. Photon spin is the quantum mechanical description of light polarization, where spin plus 1 and spin minus 1 represent two opposite directions of circular polarization. Thus, light over defined circular polarization consists of photons with the same spin, either plus 1 or minus 1. Spin represents polarization for the factor bosons as well. For fermions, the picture is less clear. Angular velocity is equal by Rönnfels theorem, the derivative of the Hamiltonian, to its conjugate momentum, which is the total angular momentum operator J is equivalent to L plus S. Therefore, if the Hamiltonian H is dependent upon the spin S, dH on ds is non-zero, and the spin causes angular velocity and hence angular rotation. That is a change in the phase angle relation over time. However, whether this holds for free electron is ambiguous, since for an electron, s raised to 2 is constant, and therefore it is a matter of interpretation whether the Hamiltonian includes such a term. Nevertheless, spin appears in the Dirac equation, and thus the relativistic Hamiltonian of the electron, treated as a Dirac field, can be interpreted as including a dependence in the spin s. Under this interpretation, Free electrons also self-rotate with a step back effect understood as this rotation. Particles with spin can possess magnetic dipole moment just like a rotating electrically charged body in classical electrodynamics. These magnetic moments can be experimentally observed in several ways. For example, by the deflection of particles by homogeneous magnetic fields in a Stern-Gallac experiment, or by measuring the magnetic fields generated by the particles themselves. This episode is brought to you by Cisco Educational Premium. Did you know that Stokes' law is a mathematical equation? The equation expresses certain velocities of small spherical particles in a fluid medium. The equation was derived in 1851 by Sir George G. Stokes and can help us understand miracles like why the raindrop does not kill us even though they are falling from tremendous heights. Looking at Stokes' law equation, the symbol F is the viscous drag. The R you see there is the radius of the sphere falling through the fluid. N is the fluid viscosity and V is the velocity of the sphere. F is equivalent to 6 pi. That symbol that looks like nRV. How do we derive this equation? We know that viscous force acting on a sphere is directly proportional to the radius of the sphere r. Coefficient of viscosity, a constant, obviously, is this symbol that looks like an N, but with one leg being short. We call this eta in Greek. It is a Greek symbol. And the velocity of object falling is v. Mathematically, we can represent this as F to be proportional to eta sub A, R sub B, R sub B, phi sub C. Okay. Let us find the values of A, B, and C. So substituting the proportionality sign with an equality sign, we get F is equivalent to K eta sub A R sub B phi sub C. Notice that we have introduced proportionality constant because we have removed our proportionality sign. Let us call this our equation 1. In this equation, K is the constant of proportionality. Then now writing the dimensions of parameters on either side of the equation, we get square bracket MLT raised to negative 2 closing the square bracket is equivalent to opening the square bracket ML raised to negative 1 T raised to negative 1 closing the square bracket raised to A is equivalent to square bracket L closing the square bracket sub B square bracket LT raised to negative 1 closing the square bracket sub C. Simplifying this, we get square bracket MLT raised to negative 2 bracket is equivalent to M raised to A dot L raised to negative A plus B plus C dot T minus A minus C T raised to negative A negative C. Let us call this our equation 2. Now we know that in classical mechanics, mass, length, and time are independent entities. Now equating the superscript or subs of mass, length, and time respectively from our second equation, we obtain A to be equivalent to 1. Let's call this equation 3. Negative A plus B plus C is equivalent to 1. Let us call this our equation 4. And negative A minus C is equivalent to negative 2. Or A plus C is equivalent to 2. Let's call this our equation 5. Now substituting the equation 3 in equation 5, we obtain 1 plus c is equivalent to t. And so c is equivalent to 1. Let's call this our equation 6. Now substituting the value of equation 3 and 6 in equation 4, we get negative 1 plus b plus 1 is equivalent to 1. Then doing some simplification, as it is obvious, b is equivalent to 1. Let's call this our equation 7. Now substituting the value of equation 3, 6 and 7 in equation 1, we obtain f is equivalent to k eta r v. And to obtain those other terms in the Stokes equation, it has been observed by and determined by experiment that the value of k for a spherical body has been determined as 6 pi. And thus the equation gives the viscous force on a spherical body falling through a fluid. So we have F is equivalent to 6 pi eta RV. Now let us come to our raindrop. Initially it accelerates due to gravity. As the velocity increases, the retarding force also increases. And finally, when the viscous force and the buoyant force is equal to the force due to gravity, the net force then becomes 0. So does acceleration. The result is that the raindrop then falls with a constant velocity called terminal velocity. On equilibrium, terminal velocity v sub t summarized by the equation v sub t is equivalent to 2r square bracket rho minus sigma bracket g on 9 eta. The simple rho is the sphere mass and sigma is the fluid mass. The Stokes law equation was first derived in 1851 by George Gabriel Stokes. No wonder the name. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.